is start off using the sandwich theorem, which we should now be at least moderately familiar with, to prove this limit. The limit as x approaches 0 of sine x over x, that it equals 1. This little picture drawn here with a circle on an axis and some triangles and all this good stuff. And we're going to use this to prove it in conjunction with the sandwich theorem. But before we do that, we're going to quick Desmos just to remind ourselves of what the graph of this function looks like. X over x. So this is the graph, and a day or two ago we said, well, it sure looks like as x approaches 0, that limit is 1, but the function's actually indeterminate there because the sine of 0 is 0, and if x is 0, that's 0 over 0. So we can't be sure without doing some extra work. So we're going to do that extra work today. So we're going to try and figure this out. So what we're looking for is above this and a function that is always below this that we can sandwich this function between. So that's going to be our goal. So we can find a function always below that has the same limit at x equals 0 of 1 that we're looking for. Started is with this little picture, and I'm going to tell you a couple things about this picture. I'm going to say that this radius of 1. So I'm going to tell you right there that that equals 1. And from there, I'm going to ask you to tell me basically the lengths of stuff as you could possibly tell me. There. Diagonal right here.
Also equals 1.
Also equal 1. This height right here. Angle x.
Sine x.
X.
Cosine x.
Sine x. Right triangle. It's the opposite leg over the hypotenuse, right? Sine is equal to opposite over hypotenuse. The mic's cutting out. And nobody's responding to me.
Yes, it's cutting out a lot.
Yeah. Let me try and fix that real quick. No. What about now? Can you guys hear me all right now?
Yeah,
Yeah.
that's better.
All right, cool. Sorry about that. I don't know what the deal with that was. I disconnected my headphones and put them back, reconnected them with the Bluetooth. So hopefully it works. If I start cutting out again, just start yelling at me in the chat and I'll try and figure it out. So why is this vertical piece here sine x?
Because sine is opposite over hypotenuse, and then the hypotenuse is equal to 1, so it's just sine over 1, so that's just sine x.
Exactly, right? This angle is x. The sine of this angle should be opposite over hypotenuse. Hypotenuse is 1, so that opposite leg has to be just sine. Now, we're not really going to use this, but what should this little one down here be? Should be cosine x, right? Do you guys agree with that?
Yeah.
Okay, cool. What about this up here? What should that one be? If this angle is still x, and let's call this here a right triangle again, right? This is a right triangle here. What trig function gives me opposite over adjacent?
Tangent.
Tangent, right? So this is tangent over 1, right? Because this length here is 1. So this piece out here should be tangent of x. Everybody feel okay about that?
Yep.
All right, cool. From there, we should be able to figure out everything I want you to figure out. So I'm going to highlight 3 different pieces of this picture. And we're going to start with this triangle right here. So that triangle, I want to know what its area is.
Sine x over 2.
All right, it should be sine x over 2 because the area of a triangle is 1/2 of base, which is 1, times height, which is sine x. So that green triangle has an area of sine x over 2. All right, next thing I want to know is the area of this big triangle.
Tan x over 2.
That one should be tangent x over 2. Same concept, right? 1/2 base times height. Now the last thing I want to know is this sector of the circle. I want to know its area. And that one might be a little bit more difficult, maybe. How do we find the area of a sector of a circle?
Area times angle over 360, right?
Yes, it's the area of the full circle, which is what? Pi r squared, times the angle itself divided by the full way around the circle, which is 360 degrees. But whenever we're trying to do this with real numbers, we need to do it in terms of radians. So we're going to say x out of 2 pi radians. And what's the radius of our circle?
1.
1. So this r squared just becomes a 1. So we got a pi here times x over 2 pi. Cancel out the pi's. What do we end up with as the area of the sector of that circle?
X over 2.
Just x over 2. Now, we've got 3 different things here. And how could we relate those 3 different areas? Tell me about the green one in relation to the red one.
It's smaller.
It's smaller, right? It's definitely smaller. I'm going to say less than or equal to because we're using the sandwich theorem and we like to have that equal to in there. What about the red and the blue one? The red one should be less than or equal to the blue one. Would you guys agree with that also?
Mm-hmm.
Cool. So now all we have to do is use this nice inequality that we've got, but turn the middle of it into sine x over x. Because if I can turn the middle of it into sine x over x, and then I can evaluate the outside pieces of it, and they're the same, well, then the middle one should be the same also. So first thing that we should do, maybe to kind of simplify this down a bit, is get rid of all those over 2's. Those can just be eliminated, right? Sine x is less than or equal to x is less than or equal to tangent x. Everybody okay with that?
Yep.
Okay. Well, then I need to introduce a sine x into the middle of this. So I think the easiest way to do that is to turn the middle into x divided by sine x, because if I have x over sine x, that's almost what I need to have. I almost have sine x over x. I would just have to flip it and take the reciprocal, right? So let's divide all of these by sine x. And it's okay for me to divide all of those by sine x because we're looking in the first quadrant right now. And so anywhere in the first quadrant, the value of sine x is positive. So I'm dividing by a positive value, which means nothing needs to happen to my inequality signs. I don't need to split it into extra cases or anything. Like we did yesterday, right? We had to split this one into multiple cases because we multiplied by x cubed, which is sometimes positive and sometimes negative. Well, in the first quadrant, sine is always positive. So that's okay. What does the left become? It just becomes 1, right? Less than or equal to x over sine x. And then less than or equal to, what does tangent x over sine x simplify to?
1 over cosine x?
1 over cosine x, exactly. All right. And now all I have to do is flip all 3 pieces of this. Take the reciprocals of all of them. Reciprocal of 1 is 1. Reciprocal of x over sine x is sine x over x. And the reciprocal of 1 over cosine is just cosine. So now I've got the function I want in the middle. But what has to happen with these inequality signs? Anytime you take the reciprocal of every piece of an inequality, the inequality signs flip. So we got to make sure we do that. Then what? What do we need to do next? We need to look at the limit as x approaches 0 of 1. And what is that limit?
1, right? Because limit of constant is constant.
Right, the limit of a constant is a constant, so that's just 1. And on the right-hand side here, the limit as x approaches 0 of cosine x, well, that's just cosine of 0. And what's the cosine of 0? Should just be 1. And so if the one that's always greater than it is 1, and the one that's always less than it has a limit of 1, then the one that's sandwiched between them must also have a limit of 1. And so we've now used the sandwich theorem to prove that that's true. Everybody feel okay about that? No issues there? Okay. What about if we took a look at this one? What's the limit as x approaches 0 of 1? This one's limit as x approaches 0 is 1, right? What about this one? What's the limit as x approaches 0 of that?
Also 1.
Also 1. So we could also make the conclusion that this one, x over sine x, its limit as x approaches 0 is also 1. Everybody see that? Any questions, problems, issues with that? All right, let's take a look at this first problem where we're going to apply this rule. So take a look at this one, think about this one for a second. I gotta help my son with something for about 30 seconds probably, and then I'll be right back. All right, sorry about that. I know that was more than 30 seconds, but sorry. All right, so any ideas on this limit here? Anybody, any thoughts on that? It looks similar to the one we just found, right? You guys want to draw another circle and label a bunch of stuff on it and do the same sandwich theorem thing? Can you guys hear me at all or no? Is my voice breaking up again? Can you guys hear me all right?
Yeah, we hear you.
Okay, you're just ignoring me. I see. Okay, just nobody's responding. Nobody has a good idea. All right. It does look similar to what we had before, but I'm guessing you probably don't want to go through and do that same process, right? That's kind of a lot of work. You guys agree?
Yeah.
Yeah. Okay. So before we had sine x over x, but now we have sine 5x over x. What if I made this sine 5x over 5x? Could I do that? Can I just rewrite it like that? Is that okay?
I don't think that would work because you'd have to do like 5 over 5, right? You'd have to multiply it like that.
All right, well, let's do that then. All right, so now I made this 5 sine 5x over 5x. Can I do that? That'd be okay, right? Put a 5 in the numerator and a 5 in the denominator?
Yes.
Yeah, I think that'd be okay. So if I've done that, then what do we have going on? We've got something right here, this sine 5x over 5x that looks very similar to what we had before. Could we assume that this limit is 1? Probably not. We probably can't assume that, even though it might be 5. Maybe it's like a fifth. Who knows? But we could probably use a little trick to evaluate this piece of it if there wasn't a 5 in front of it. Can I get rid of that 5 in some way so that it's not in the way?
Yeah, can't you put it out in front of the limit? Like you can
I
move the
can.
constant.
Exactly, yes. There was a rule that we talked about yesterday that was you are allowed to take a constant that's in front of a function and move it outside of the limit. So we can make this 5 times the limit as x approaches 0 of sine 5x over 5x. Everybody good with that?
Mm-hmm.
All right, awesome. So next thing then is how do we deal with sine 5x over 5x? Could I somehow turn 5x into a different variable? Could I just do something like this? Let's let u equal 5x.
Yeah.
If I do that, I got 5 times the limit, and I'll deal with that x approaches 0 in a second, of sine of u over u. Sine of u over u would be great if my limit was u approaching 0, right? Because then I would know that this was 1. But do we know that u is approaching 0? We know that x is approaching 0, right? Well, if x is approaching 0, what is u? U is 5 times x, right? So if x is approaching 0, what can you tell me about u? U must be approaching
0, right?
0 also, exactly. So we could rewrite this if we let u equal 5x as 5 times the limit as u approaches 0 of sine u over u. And what's the limit as u approaches 0 of sine u over u?
1. And then
1.
times 5 is 5.
5 times 1 gives us 5. Everybody feel okay about that?
Yeah.
Any questions there? All right, let's do another one. That's a little bit more difficult. How's this one different?
It's sine of y, but x approaches 0 instead.
Oh, right. I keep forgetting that I made a typo on this. Good. Let's make that a y. All right, now how is this one different?
There's a power in it.
All right, that's what I was looking for, is we got a power in it, right? We got the sine cubed of 4y, and we got a y cubed in the denominator. So if the numerator, sine of 4y, is being cubed and the denominator is being cubed, can't I put that cubed around the whole fraction? Isn't it the same thing?
I believe so. Yeah.
Yes, 100%, that is definitely the same thing. So what do I need in the denominator there to make this a limit that I know how to deal with and evaluate?
You need a 4.
I need a 4. So I'll put a 4. As long as I put a 4 in the numerator, that should be okay, right? Would everybody agree that that's okay?
Mm-hmm.
Okay. Cool. So before we had a constant in the numerator and we pulled it out in front of the limit because it was in the way. Can I do that now?
You can't, I don't think.
Could
I
you
can, but say that again?
Oh, could you like multiply it? Like, could you cube it first and then take it down?
Exactly. So I can pull this 4 out, but when I pull the 4 out, it's not actually a 4 because it's not only getting pulled out of the limit, but it's also getting pulled out of these parentheses where it's being raised to a third power. So really, when I pull the 4 out, I'm pulling out 4 to the third power, pulling out 64. And then I've got the limit as y approaches 0 of sine of 4y over 4y. And everything inside the limit is being cubed. And if everything inside the limit is being cubed, I believe we had a rule about that yesterday, that I could take that cubed and pull it out in front of the entire limit, or out on the entire limit. You guys remember seeing that rule yesterday? Maybe somewhere in here. There it is. All right, if I have this limit, the limit is x approaches a of f of x to the n, I can make the whole limit be to the power of n. Everybody good there?
Yep.
Okay, so what's inside the brackets should be easily evaluated. What is what's inside the brackets equal?
1.
Should be 1. The reason it's still 1 is that same thing. We could do a substitution and replace the 4y's with a variable and show that that same variable is approaching 0. But from now on, you're not going to have to show that. I would tell you anytime it's a limit as the variable approaches 0 of the sine of something over that same thing, it's always going to just be 1. So this just becomes 64 times 1 cubed, or just 64. Easy enough. Any questions on that? Okay. I can't tell if somebody's trying to talk. If somebody's trying to talk, I can't hear you. It's cutting out really bad. Maybe they're not. Let's take a look at this one. If you have a question and I'm not answering it, it's because I can't understand what you're saying or hear you. So just type it in the chat if you have a question and I don't answer right away. So take a look at this one, see if you can come up with a way to get this one started. I'll give you 30 seconds or a minute or so to think about it, and then we'll talk about it. Anybody have an idea of how to start this one?
Can you take out the 4 first?
All right, the 4 that's in the denominator there? Yes. So if we take this 4 out, it's not actually a 4, right? It's actually a 1/4. Right, because it's in the denominator. So we got 1/4, the limit as z approaches 0. And that's going to give me a z to the 12th and then a sine 3z cubed to the 4th. Could I pull the 4th out of the numerator and make it sine of 3z cubed to the 4th?
You can manipulate the z12 to like z to the 3rd times z to the 4th.
Even better. Or not z to the 3rd times z to the 4th, but z to the 3rd to the 4th
To the
power, right? Right, exactly. So here I've got sine 3z cubed to the 4th, just like I have in the numerator, and I've got z cubed to the 4th, which is z to the 12th, still in the denominator. And I've got that 1/4 that was in the denominator pulled out in front. Everybody feel okay about that? Okay, so next step is throw the 3 in the denominator, throw the 3 in the numerator, and pull that 3 out. But that 3 is not actually 3 when I pull it out. What is it?
81.
It's 81. It's 3 to the 4th power, right? So this becomes 81 over 4 times the limit as z approaches 0 of sine of 3. That's not a 3. 3z cubed over 3z cubed. And that whole limit can be raised to the 4th power, which gives us 81/4 times 1 to the 4th, or 81 over 4. Good. Any questions on that? All right, let's move on to the next one. Any thoughts on this one?
Are you allowed to subtract the 2y at all? Or
No, we cannot subtract a 2y. We can't just get rid of stuff. Even if we were to like subtract, we'd have to add another 2y into it to keep it sort of at its equilibrium there, to keep it where it started. So we can't do that. We're gonna have to use some of those rules that we had from yesterday.
Can you write them as 2 separate fractions?
Sure, what 2 fractions do you want to write them as?
2y over 4y plus sine of 3y over 4y.
All right, limit y approaches 0, 2y over 4y, plus limit as y approaches 0 of sine 3y over 4y. Everybody good with that? So we did the 2y over the 4y, and we did the sine 3y over the 4y. 2 separate fractions, separated them out as 2 separate limits. Well, what's the first one? 2y over 4y. If I plug in 0, what do I get? 0 over 0. But I should be able to just quickly cancel out the y's, which will give us what?
1/2.
1/2 plus, and what am I going to do with this sine 3y over 4y limit?
You can multiply by 3 over 3, right?
I will do that, but I still have this 4 down here, so can I pull that 4 out?
1/4, right? Because
Yeah. Yep. Pull out the 4 as a 1/4, and then we get 3 sine 3y over 3y. Everybody good and following along with that? Next up, we'll pull the 3 that's in the numerator out, making that a 3/4. And then we got the limit as y approaches 0 of exactly what we need in there, sine 3y over 3y, which is just 1. So we've got 1/2 plus 3/4 of 1, or 1/2 plus 3/4, which is 5/4. So we see how those rules can help us to manipulate some of these trig ones to give us different limits that we can easily evaluate. Yeah, any issues there? Any questions with that? All right, let's do some more. This one's a little bit different. And tell her thank you.
Thank you.
Sorry, talking to my kid there for a second. Trying to teach him how to be polite with his teacher. Any thoughts on this one? Totally different, right? No sign in this one, is there?
Oh wait, but there could be if you could square it and then it could be equal to sine squared x. I don't know if.
You mean if it was 1 minus cosine squared x? Is that what you're saying?
Yeah.
Okay, that's a good thought. We could introduce a sign in there by using a little bit of manipulations with our trig functions. So how could I turn 1 minus cosine x into 1 minus cosine squared x? What would I have to multiply it by to get that?
1 plus cosines x.
Yep, that would do it, because then that would be a difference of squares, right? So we're going to make this the limit as x approaches 0 of 1 minus cosine x times 1 plus cosine x. And if we do that to the numerator, then we got to do it also to the denominator. So limit as x approaches 0 of 1 minus cosine squared x over x times 1 plus cosine x. Everybody so far good with that? Okay. And then the 1 minus cosine squared is going to turn into sine squared.
No. What do you need to do? I just need to do this.
Now what?
I'm gonna go,
Can you factor out? Can you like take the 1 plus cosine x, or no, because there's a variable?
It's got a variable in it, so it is not a constant. It cannot be pulled out. We got to leave it in there. Although if we think about the 1 plus cosine x, the 1 plus cosine x isn't that big of a problem, because if I plug in 0 to it, it's just 1 plus cosine of 0. It's just 1 plus 1. It's just 2, right? And that's not a problem. It's when we have a 0 down there that's a problem. It's this x that is 0 that's causing the issue.
Oh wait, could you, so if that's a 2, could you pull out a 1/2 from the whole thing and then you have sine squared of x over x, which is closer to what you'd want?
Unfortunately, well, I guess we could, yeah, we could do that. It's kind of a roundabout way, but yeah, we can rewrite it first. We'd have to do it this way. We'd have to rewrite it as sine squared x over x times the limit as x approaches 0 of 1 over 1 plus cosine x. Kind of ran out of room there. And now, what is that limit as x approaches 0 of 1 over 1 plus cosine x is just 1/2, right? So we've got 1/2 of the limit as x approaches 0 of sine squared x over x. So that's fine. Now we've got rid of the 1 plus cosine x by writing it as a separate limit. But you can't just pull the 1 plus cosine x out until you've evaluated that piece of it. Everybody okay with that step? Okay, so then what? Now I got sine squared x over x, which isn't quite what we need. We would need it to be sine of x over x all squared, but I can't just put another x in here without putting an x up here. Do we want to try and do that, or what do you guys think?
Well, it's fine to have an x there, right? Because like if it's in the numerator, that's okay. It's not going to mess with things.
Okay, so how can I evaluate this then? Because right now I have 0 over 0 still, right, if I plug in the zeros. Can I separate out the sine squared x maybe? What if I did this? Would that be okay?
That works.
That seems like that'd be all right. What's this first limit going to equal? Sine x over x is
1.
1. And what about the limit as x approaches 0 of just sine x? What is that?
0.
0. So when I multiply all these together, what do I get?
0.
0. So this limit is 0. This is another one that you're going to want to know and have memorized. Any questions on how we got there? Okay. I'm not going to prove this one right now, but just a point to note, and I'm going to write out all the ones you should know at the end of the day today. This one, if you flip around the 1 minus cosine x to become cosine x minus 1, that limit is still 0, cosine x minus 1 over x. So you should have these two memorized also. Next two things to know. Any questions there? Everybody okay there? Anybody feeling lost? With the math, not just in life. Let's do this one. The limit as x approaches 0 of 1 minus cosine 10x over x. Thoughts on this one? Anybody? Anybody have an idea on this one? Think back to this one. What did we do with the limit as x approaches 0 sine 5x over x?
We
We
made
had
the bottom the same thing as like this stuff in this sign.
Exactly. And so we probably need the same thing here. We need the bottom to be the same as the stuff in the cosine, right? So let's do that. Let's make this the limit as x approaches 0 of 1 minus cosine 10x over 10x, which means I got to multiply the top by 10. Yeah? And this 10 in the numerator can be pulled out. 10 times the limit as x approaches 0 of 1 minus cosine 10x over 10x. And once again, using a simple substitution, if we were to let u equal, I'm going to write it out this time, if we let u equal 10x, then that means u is approaching 0 as x approaches 0. And this limit would become 10 times the limit as u approaches 0 of 1 minus cosine u over u. 10 times 0 gives us 0. So I did the substitution again since this one wasn't with the sine x over x, just to make sure it works. So now we know it works for the 1 minus cosine x over x ones, and you don't need to write it out either anymore. We get the idea on that or no?
I don't get how you get from like the answer, or from the second to last part, the answer. Yeah, so right there
Right
to
here?
10 times 0. Yeah.
Okay, so this limit right here, the limit as u approaches 0 of 1 minus cosine u over u is this one that we just proved back here, right? The limit is x approaches 0 of 1 minus cosine x over x. We just have all the
1
x's
minus
as
1,
u's.
right?
And,
Or
well, no, so it's an indeterminate limit, but right, if you plug in 0 to it, it becomes 0 over 0. But we went through this process to show that
yeah.
it actually is 0. So now we've proven that this is 0. We don't have to prove it every time. If that limit shows up anywhere within the work we're doing, we can just say, all right, that part's 0.
All right. Yeah.
Does that help?
Yeah.
Cool. Any other questions on that one? All right, let's look at another nice easy one. This one looks simple and straightforward, huh? No. John says no in the chat. No, it doesn't. You're right. It doesn't look that simple and straightforward. So what are we going to do with it?
The top, isn't it like the triangle thing? I don't remember the name for it, but it's like the 14641 thing.
That is exactly right. The top is that triangle thing that you don't remember the name of. Let's write out that triangle thing that you don't remember the name of. It's Pascal's triangle. Does that sound familiar to people?
Yes.
Oh, good. Pascal's triangle. Hopefully you're familiar with it a little bit. I'm going to write out, I'll just write out that much of it. It goes on infinitely forever. But it starts with a 1, and then the next two are a 1 and another 1. And then as you go down each row, the outsides are always going to be 1s. And then everything on the inside you get by adding the numbers surrounding it above. So the 1 and the 1 make 2. And here the 1 and the 2 make 3, and the 2 and the 1 make 3. And the 1 and the 3 make 4, and the 3 and the 3 make 6, and 3 and the 1 make 4, and so on. And there's a lot, I mean, there's a ton of different uses for Pascal's triangle. But the most important to us is that it is used as the coefficients for binomial expansion. So a plus b to the 0 power equals what? It equals 1, right? What about a plus b to the first power? Well, it's just a plus b. And what are the coefficients of a and b? They are 1 and 1. And if we go down here, what are the coefficients when I do a plus b squared? Well, a plus b squared is a squared plus 2ab plus b squared. And the coefficients are 1, 2, 1. That's our second row. This is row 0, row 1, row 2. Our third row should be the coefficients if we expand out a plus b to the third, which is a cubed plus 3a squared b plus 3ab squared plus 1b cubed, 1, 3, 3, 1. And same down here. This one is a to the fourth plus 3a cubed b plus, why am I doing threes? Sorry, the fourth one. A to the fourth plus 4, a cubed b plus 6, a squared b squared plus 4ab cubed plus 1b to the fourth. And so those are the same coefficients we've got in that problem we were working on. Although we'll note that these two were minuses in the one we're looking at, right? 1 minus 4 cosine x, then plus, then minus, then plus. So if we want to expand out a minus b to the fourth, we take the minuses. And if we want to expand out a plus b, we take the pluses across the top. So this will help you expand out any binomial. If you want to, if you want to expand out, let's say x plus 2 to the 5th power, your answer should be the first thing, x to the fifth, and then it should be plus 5 times x to the fourth times 2, that being our b value, and then plus 10 x to the third times 2 squared, and then plus another 10 times x squared times 2 cubed, and I'm out of room, but then 5x and times 2 to the fourth plus 1 times 2 to the fifth. You should be able to expand out any binomial to a power using the rows in Pascal's triangle. Does that look familiar to you guys?
Yep.
All right, good. So now when you look at this, you should be like, 1, 4, 6, 4, 1. That's the fourth row of Pascal's triangle. And it alternates positive, negative, positive, negative, positive. So that must factor down to 1 minus cosine x to the fourth power. And since I have 1 minus cosine x to the fourth and x to the fourth, I should be able to rewrite this as 1 minus cosine x over x, all raised to the fourth power. Everybody feel okay about those couple of steps now that we've looked at Pascal's triangle? And what does that become? The inside of the brackets is just 0 from the previous problem. 0 to the fourth is 0. Any questions on that? All right, let's do another one. We just got 2 more. We're only going to do 2 more problems today, and then we're going to be done. We might get done early. Look at that. That's exciting. Any ideas for this one? No ideas there?
We're not allowed to take out the sign, are we?
Nah, you can't take out the sign. Let's see, in the chat, we got double angle identities. Double angle identities. Those sound like a lot of work that I don't want to do right now, John. Yeah, we can't take out a sign. We can't, I mean, we could do some double angle stuff, but man, that's going to be a lot of work. Let's just rewrite this as the limit as y approaches 0 of sine 4y over 1 times 1 over sine 10y. Is that the same thing?
Yeah, they're the same thing.
Yeah, it's the same thing, right? Now, the first part of that, sine 4y over 1, if I could get a 4y in the denominator there, that limit would be very easy. True? Just the first part of it.
Mm-hmm.
And what if I could get a 10y in the numerator, the second part of it? That'd be a very easy limit to evaluate also, wouldn't it?
Yeah.
Yeah, so, well, let's just do that. I could put a 4y in the denominator, right? I'm just going to put what I need into the problem. I need a 4y. I need a 10y. And then let's make sure that we haven't broken any rules. So I put a 4 in the denominator. Did I put a 4 in the numerator?
No.
Nope, I better do that. Okay, done. All right, I put a y in the denominator. Did I put a y in the numerator?
No.
I didn't. There's a y right there. Didn't I put that up there?
Oh,
Yeah, I
wait.
put a y up there also, right? I know these are separate fractions now, but it's all multiplied together, right? I put a 4 down here, I got to put a 4 up here. If I put a y down in the bottom, I got to put a y somewhere up in the top. Since it's all multiplication, it doesn't really matter which side it's on, does it? Shouldn't matter which side it's on, because I can always put all this right back together and make this a 40y up here that I'm putting in the top. You guys see that? And since I put a 10 in the top, I got to put a 10 in the bottom. And so effectively, I've multiplied the numerator by 40y and the denominator by 40y. Good or no?
Can you do that again?
Sure. All right. So we know that we need to put a 4y down here. Right, and we know that we need to put a 10y up here. So I put a y up in the numerator and I put a y in the denominator. Those are good. Those cancel out. That's y over y. That's 1. It doesn't matter that one's in this fraction on the left and the other's in this fraction on the right, because it's all being multiplied. I could just make this all one big fraction, can't I? If I wanted to. So the y's are good, but the 4 doesn't have a 4 up here. Now it does. And the 10 doesn't have a 10 down here. And now it does. Does that make sense to everybody or no?
Yes.
Yeah? All right. So the 4y in the denominator needs to stay, but the 4 in the numerator needs to get pulled out. And the 10y in the numerator needs to stay, but the 10 in the denominator needs to get pulled out as a 1/10. And so then I've got two different limits that are being multiplied together. I can separate them into their own limits, sine 4y over 4y. And the limit as y approaches 0 of 10y over sine 10y. And what happens to this one? The first limit is
1.
1, and the second limit is?
I guess also 1, because it'd be like the reciprocal of 1, which is 1.
Yep, yeah, and that was one of the ones, remember back when we first proved this, I said that x over sine x, that one also comes out to be 1. We did this little extra work there. So 2/5 times 1 is just 2/5. Everybody feel okay about that? Any questions on that? All right, we got one problem left to go then. Hopefully you're all feeling all right.
I'm curious.
Any ideas on this one?
Could
Similar,
you like
but
separate them with like the division and multiplication thing again?
sure. Okay, so, and you want to leave them as tangents? Let's leave them as tangents. That sounds good. Limit as x approaches 0 of tangent of 3x over 1 and 1 over tangent of 4x. So what can I do here? This tangent is really what? Sine over cosine. So I could make this sine 3x over cosine 3x, and 1 over tangent is really just cotangent, which is cosine 4x over sine 4x. And then how does this help me? I mean, it's almost the same as the problem we were just working on, right? With the sine in the numerator and the sine in the denominator, except I got all these extra cosines in here that are kind of messing things up. can I move the cosines out to the end so that I can just deal with the sines like I know how to, and then see what happens with the cosines? Something like that. Is that okay? I mean, am I allowed to do that or no?
Yes.
Yeah, I should be able to. So that at least will let me deal with the first two fractions here. I need to put in a 3x, and I need to put in a 4x. And if I put a 3 in the denominator, I need a 3 in the numerator. If I put a 4 in the numerator, I need a 4 in the denominator. So what constant's going to get pulled outside this limit?
3/4.
3/4, good. So 3/4 times the limit as x approaches 0 of, well, let's write each piece of this as its own limit. Sine 3x over 3x. Limit as x approaches 0 of 4x over sine 4x. And the limit as x approaches 0 of cosine 4x over cosine 3x. 3/4 is still just 3/4. What's the first limit?
1.
This one's 1. What's the second limit?
1.
1. And what about the third one?
Also 1.
Also 1, because as I plug in 0 to this isn't indeterminate. This is just a limit I can evaluate. The cosine of 0 is 1. And in the denominator, the cosine of 0 is 1. So this is just 1 over 1. Right? 3/4 times 1 times 1 times 1 gives us 3/4. How do we feel about that? Okay? Or no? Any questions? All right, real quick. There are 6 different trig limits I want you to have memorized. So we've talked specifically about 4 of them. This one is 1. This one is also 1. We had 1 minus cosine x over x. That one was 0. And then I briefly mentioned, but we didn't use this one, cosine x minus 1 over x. That one's 0. And the other one we're going to say, or the other 2, are these. Tangent x over x is also 1. And the limit as x approaches 0 of x over tangent x is also 1. And these 2 at the bottom that we haven't really talked about can be proven using the same idea of what we were just talking about, right? If I have tangent 3x over tangent 4x, and I'd separated that out like this, the cosines end up not mattering from the tangent, and it just effectively becomes the same as the sine one, because the cosines, when I take the cosine of 0, all just become 1s and, you know, cancel out with the rest of it. Does that make sense? Cool. That is it for today. We're done 7 minutes early, I think. I think we're supposed to be done at 12:50. Just out of curiosity, do your other teachers